So it's a pleasure to introduce our next speaker, Professor Alix McCollam from Radboud University in the Highfield Lab in Nijmegen. Alix did her PhD in Cambridge with Steve Julian, followed by a postdoc in Toronto before a Marie Curie fellowship in Nijmegen and now a professorship. And Alix is well known for her work on a range of strongly correlated and topologically ordered materials, including cerium, cobalt, indium, iron selenide, strontium titanate, uranium platinum 3, and so on. And she performs measurements using transport and quantum oscillations to reveal the underlying ordering and indeed sometimes hidden ordering in these materials. As it happens, we both have a familial connection to the small village of Balik in Ireland. But today, Alix is going to tell us about heavy fermions in high magnetic fields. And it's a great pleasure to hand the floor over to you, Alix.
Okay, thank you, Andrew, for the introduction. And thanks, of course, to the organizers for giving me the chance to speak at this quite remarkable meeting. It was supposed to be summer school in Skye this week, which it's a bit disappointing that we're not there, but this is really something special, I think. So it's a pleasure to speak today. So the title that I gave is Heavy Fermions in High Magnetic Field, and it's not the most original title. Indeed, I was a little bit sheepish about it. But I think the idea is that I will give some kind of general introduction, thinking about how we look not necessarily just at heavy fermions, but in high magnetic fields. And then I'll focus on some work that we've done reasonably recently on family, the cerium 115 family and related materials there. Okay, so this is a very brief outline. I will give or try to give a kind of general introduction and then think about heavy fermions in high fields, a very short discussion about quantum criticality, really in the context that's relevant to the data and the research work that I will then show you. And then I will talk about this family of cerium-based heavy fermion materials. So the 115, cerium, rhodium, indium 5, cerium, cobalt, indium 5, and cerium, indium 3, of course, are part of this family. But I will talk mostly about cerium, platinum 2, indium 7. If you have questions, please stop me. As I said, this was supposed to originally be a kind of pedagogical talk, and it morphed into a cross between that and a research talk. So in an hour, I can't cover everything and I won't manage to say everything. So if there are questions, please do stop me. I will look at the chat and try to answer any questions that come up there. Otherwise, you can raise your hand and Andrew or one of the organizers will notice you, I think, and interrupt me. Okay, so heavy fermions and f-electrons. So there are many correlated electron systems and they all have very interesting properties, but the things that set the heavy fermions apart or that makes them different to others is the behavior of the f-electrons or the properties of the f-electrons. So these come in the ones that we care about from the lanthanide and actinide group. So it's the 4f and the 5f electrons. This is just a snapshot or a section of the periodic table. The main ones that we look at in the heavy fermion systems are the cerium and praseodymium-based compounds. I've given the outer structure, shell structure here. So there's one 4f electron, two 4f electrons, etc. The s and the d electrons are typically conduction electrons in these materials, in the metallic elements and also in the intermetallic, so in cerium or heavy fermion or f electron-based intermetallics. The f-electrons can be localized or, as we'll see, they can be part of the Fermi surface depending on the interactions in the material, the interactions particularly between the f-electrons and the conduction electrons. In the actinides, the main creatures that we think about as the uranium and neptunium, there are also plutonium compounds, but they're a lot less widely studied, perhaps for obvious reasons. So this is a reminder of the f orbitals. And the thing about the f electrons is that they're spatially rather close to the core, the nuclear core. So the f electrons tend to be localized near the nucleus or near the atomic core, but energetically they're quite almost degenerate with the s and the d electrons. So spatially localized, but energetically quite comparable to the conduction electrons, which allows for this interactions between the f electrons and the conduction electrons that make the behavior of these materials special. Okay, so now my page doesn't shift. Ah, that's interesting. I'm trying to turn the page, but it's not turning. Okay, this worked 2 minutes ago, didn't it?
Or just try quitting and going back.
Yeah, hang on a minute. I'll just stop. Actually, the whole thing has frozen. Okay, bear with me, small glitch. Okay, I might have to leave the meeting and come back, or stop sharing the screen at least, because this is completely frozen.
No problem.
I can't even do that. Okay, give me a minute.
Okay.
Piers, I think she's completely frozen. Is it worth you manually quitting her sharing screen?
Yes, I was trying to do that actually.
Yeah, that works. So when she comes back, she should be able to do it again without an issue.
Okay, I'm back. Now let me get my talk back. Okay, do we have it back?
Yes, that's
Yeah,
fine.
we're back. We're back.
Back in
Okay,
business.
I'm sorry about that. Okay, so we were just here, and I'll continue where I left off. So the heavy fermion materials are intermetallics with these lanthanide and actinide materials. And the things that really stand out in their properties that we're most interested in, or that characterize them as heavy fermion systems, are especially the following. So I'm talking about experimental quantities now, and I'll talk a bit later about what actually makes them behave the way that they do. So at low temperature, specifically, there's a very large specific heat capacity. So this is the expression for the specific heat, where gamma is the low temperature electronic contribution, and this would be a high temperature contribution. There's also typically in a lot of the heavy fermion materials a contribution from spin fluctuations, but at low temperature we usually see a strongly enhanced gamma coefficient on the specific heat. In de Haas van Alphen and other quantum oscillation experiments, we see a large effective mass. So this is directly probing the effective mass on the Fermi surface. This is the temperature damping factor from the Lifshitz-Kossovich formalism for the de Haas van Alphen effect, and the effective mass appears in here. So if you measure the temperature dependence of de Haas van Alphen oscillations or Shubnikov-de Haas oscillations, then you can measure the effective mass. And in heavy fermion compounds, this is very heavy. This is what gives the materials their name. The A coefficient of the T-squared resistivity, when there is a T-squared resistivity, so heavy fermions are not always Fermi liquids, or do not always form Fermi liquids, but when they do, the A coefficient tends to be large. And then in the magnetic susceptibility, you have at high temperature, typically a Curie-Weiss susceptibility, and then at low temperature, this tends to saturate. Again, if it's a good Fermi liquid, you have a Pauli-like susceptibility. If it's not, you see sometimes some other behavior. So the behavior of the specific heat, of the susceptibility, they're not unique at low temperatures, but they are typically strongly renormalized, so related to a a strongly renormalized density of states. Things like thermal conductivity and many other experimental quantities are related typically to some of these quantities, so they show similar characteristics related to an enhanced density of states. Examples just to show you what it looks like experimentally and give you some numbers. So the specific heat, if you plot C over T and look for the gamma coefficient, this is uranium platinum 3, which is one of the very important heavy fermion materials, because it's one of the few that is a very good Fermi liquid, and the properties of the Fermi surface and the effective masses in the Hausmann-Alphen effect and the specific heat all correspond to each other very nicely, which is, it was a good job that there was at least one material that did that, I think, in the early days of heavy fermion physics. This is then C over T as a function of T squared. So there's no contribution proportional to T squared here. It's at very low temperature. This is low temperature. And then you see that this gamma coefficient is just a constant, and it's around about 420 millijoules per mole Kelvin squared, which is extremely high. If you consider a regular metal, so some kind of good metal like aluminium, it's only 1.2. So this is a huge enhancement. And a number of other materials like uranium, ruthenium-2, silicon-2, or cerium, copper-6, this can be even higher, up to 1,000 or even a bit more. For a free electron, the gamma coefficient is related to the effective mass in this way. So it's related to the density of states, and it's related to the effective mass in this way. So when you measure the Hausmann-Alphen oscillations and measure the effective mass in the quantum oscillations, this should represent, or it should reflect, the enhancement of the specific heat.
There is a question in the
Magnetic
chat, Alex.
susceptibility. Oh, then I see a question in the chat. Do you have cases where there are not Fermi liquids, but still you see yeah. So many of the heavy fermion systems are not Fermi liquids. They have a very, maybe T linear or T to some other coefficient exponent resistivity and quite distinctive non-Fermi liquid Pauli, etc. behavior in the various quantities, but the de Hausmann-Alphen effect seems to work one way or another. So in fact, you can just put whatever interaction you like really into the de Hausmann-Alphen. So okay, let me clarify. When you measure the effective mass in the de Hausmann-Alphen effect, you're measuring the temperature dependence of the Fermi function effectively, and that's where it's coming from. But that's for a Fermi liquid. If you don't have a Fermi liquid, you have a different form of the self-energy that goes into the expression for the de Hausmann-Alphen effect. And it will give you maybe a slightly different temperature dependence, for example, but it still allows you to see the clear de Hausmann-Alphen oscillations. So this applies to electron-phonon interactions as well as electron-electron interactions. If there are things that modify the self-energy, then it can modify things like the temperature dependence of the de Hausmann-Alphen effect if it's strong. If it's not strong, then you still see the same Lifshitz-Kossovich behavior in the de Hausmann-Alphen effect.
Thanks.
Okay, this is an example of the susceptibility. So this is chi versus temperature. Again, this is uranium platinum 3. This is a nice Curie-Weiss behavior at high temperature, and then at low temperature you see a Pauli dependence here. This is proportional to the density of states at the Fermi energy. There's also a Van Vleck contribution to the susceptibility. So the low temperature susceptibility is not necessarily unique, as I said. It doesn't always saturate in a nice Pauli-like behavior. You can see different things going on. This was quite reasonably well understood in uranium platinum 3. The Van Vleck contribution kind of explained the large size of this and the behavior here. And this is an example of data from the 115 family, cerium, rhodium, indium-5, etc. This is in the AB plane. These are tetragonal materials, and this is along the C-axis. In this case, it's hexagonal, and this one was along the AB direction, and this one was along the C-axis. And here we also have anisotropy, but you can see that there's a good Curie-Weiss behavior at high temperature, and then something else happens at low temperature, but it is large. So these are in different units, actually. So 120 here is about 10 here. So they're comparable sizes, just the units are slightly different. So they're typical magnetic susceptibility curves. This behavior, as I said, is not always predictable, but it's always large. Electrical resistivity is the other really important experimental quantity. So again, I'm using uranium platinum 3 because it is a good Fermi liquid and it's nice to see. This is the resistivity as a function of temperature has this rho naught plus a t squared Fermi liquid-like behavior of the A coefficient when you have a Fermi liquid. In this case, uranium platinum 3 is a good Fermi liquid, and you can see this plot against t squared gives you a very nice linear relationship with an A coefficient of, this is 1.55 along the AB direction and 0.55 along the C direction. The relationship to the renormalized specific heat comes through the Kadawaki-Wood ratio in that case. It's not always held, but it's very commonly observed, this ratio in the heavy fermion materials. On the other hand, ytterbium rhodium 2 silicon 2, this is the very famous phase diagram of ytterbium rhodium 2 silicon 2. This is not everywhere a Fermi liquid, so this is temperature versus magnetic field. And this color coding gives you the coefficient here. So here, instead of just 2, this is some other coefficient. In the region where this is dark blue, this is indeed a Fermi liquid. And in this region, the A coefficient is enormous. So this is A coefficient of 20, 22 at low temperature in these regions. At higher field, I've cut this off actually, but if you extend this out to higher field, going out in this direction, then this settles down at a lower number, but still relatively high, still of the same order of the enhancement in uranium platinum 3, and still significantly larger than in a regular metallic system. Okay, so why do we have these particular experimental dependencies? So these are characteristics. They're common across many heavy fermion systems. And in many cases, you can continue them in high magnetic field, right? So you can do magnetoresistance measurements, or all of these things are things that we can measure relatively easily in high magnetic field. You can also do the quantum oscillation measurements, which I didn't show here because, well, you can't actually see what the behavior of the effective mass looks like there, but it's easily measurable when you measure the temperature dependence that I showed earlier. Okay, so the f-electrons effectively form a system of local moments. I said that they're drawn in rather close spatially, at least to the atomic core. The simplest case is just you have a single unpaired electron localized at an isolated atom or ion, and you have a Curie susceptibility from that collection of moments that looks something like this, where this is just the Bohr magneton and this is temperature. M is the magnetization, this is the Pauli matrices. This gives you a Curie-Weiss paramagnetism developing, and I said that this really just appears at high temperature, but when you are at high temperature, you have something that looks a little bit like this, where this is the concentration of the magnetic moments, and this is the Curie-Weiss temperature. So if this is negative, then you have an antiferromagnet, and otherwise it's ferromagnetic. This is the angular momentum quantum number, and this is the G factor. So that's the Curie-Weiss susceptibility at high temperature. And the interaction of these local moments with the conduction electrons is what is giving us most of the physics, or most of the characteristic physics in these materials. So the conduction electrons and the moments interact. There's an exchange interaction or an antiferromagnetic interaction which has some strength. So this J is now the coupling between the local moment and the conduction electrons. So the F moment and the conduction electrons. And this develops a temperature dependence, or a form that looks like this. And when you change the temperature, so if you look at the strength of this coupling as a function of temperature, when you get to a temperature that is approximately, this size, then the second term becomes about the same size as the first term, and then you can't treat this as a perturbation of this anymore. So you have to well, it becomes more important in the behavior of the system. So this temperature is a kind of a division between a high temperature region where you have local moments and conduction electrons not doing very much to each other. And then at lower temperature, below this temperature, you have a stronger interaction. So actually you get the formation of a bound state. The interaction is strong enough that you get singlets forming between the local F moment and the conduction electrons. So a strong coupling, you get a singlet state. So in this case, at low temperature, below the Kondo temperature, which is a characteristic of the material, then you have there you typically have your Fermi liquid with the Pauli susceptibility, as I mentioned before. This is for the case of a single impurity. And when you put the local moments on a lattice, then you get a slightly different behavior because coherence develops. In this case of the impurity here, you have a gamma coefficient that becomes constant and is determined by this Kondo temperature. So as I said, if you have a lattice and not just single impurities, you can also think of this conduction electron hybridization as a constant exchange of spin flip transitions, right? You can, so this F electron has some finite amplitude of probability to tunnel flip spins in this way, and you can think of the probability of this tunneling or the rate of this tunneling as defining this Kondo temperature scale. So this is giving us basically it's the relevant temperature. There isn't actually another relevant temperature scale in this problem. So when you have a Kondo lattice or local moment sitting on a lattice, you have this type of interaction and you end up with a coherence at very low temperature, and then the relevant energy is given by the temperature, the coherence temperature, which is the Kondo temperature. So the single impurity will scatter the electrons elastically, but it's not conserving momentum. And this is what gives you the increase in the resistivity, or gives you an increase in the resistivity for this singlet impurity system. When you're on the lattice, you have the translational symmetry. So you still have the elastic scattering, but now it's momentum conserving, and you get a reduction of the resistivity once you go below this Kondo temperature. So to see how that looks like, these are some examples, kind of famous examples, I suppose. This is cerium aluminium 3. Resistivity doesn't do very much. This is resistance here, or resistivity rather, as a function of temperature. It doesn't do very much at high temperature, and then you see it starting to increase due to the formation of these, or the stronger interaction of the F and conduction electrons, and then the coherence starts to develop once you get to this Kondo temperature, and then below that the resistivity drops away. This is in cerium cobalt indium 5. This again is the same thing. This is the coherence temperature on the resistivity. This is the axis of resistivity as a function of temperature, and this curve is the resistivity curve. This is the susceptibility, which is given on this axis, and you can see that the Curie-Weiss type behavior that turns into a kind of at least temporary saturation of the susceptibility coincides with the coherence temperature also here. So these two happen around about the same temperature. This is a nice example. It's a very famous example. This is cerium copper 6 doped with lanthanum. So the cerium copper 6 is this bottom curve. And again, you see this coherence temperature and the resistivity drops at low temperature. As you take away the F electrons, so you dope with lanthanum and you're basically taking out the F electrons, then you spoil this effect. You take away the Kondo lattice and you remove the coherence, and you go towards something that looks a bit more like the single impurity problem. Lower density of moments. Okay, so in this picture, when you have local moments on a lattice and they're interacting with the conduction electrons in this way, so our lattice Kondo effect gives us a renormalized density of states. In the single impurity case, you get a resonance here, but in the lattice case, you actually get a band forming that has some finite width, which is proportional, or is approximately proportional to the Kondo temperature. You get a renormalized density of states, and this also gives you a renormalized band structure. So here I plot the energy versus momentum, and this would just be a conduction band, a relatively parabolic conduction band. This is the Fermi energy, and this would be the localized F electron levels. So as I said, they're very close spatially, sitting towards the nucleus or the atomic core, but energetically they're almost degenerate with the conduction electrons. So they sit rather close to the Fermi energy. And this would be the size of the Fermi wave vector. When you have the interaction, or when the Kondo singlets form, or when you have a strong Kondo interaction, the conduction band is then, it's renormalized, or it reconstructs due to this hybridization, and you have a development. This green one here would be the conduction band, and here it would change into the red bands. The Fermi surface would become larger, so the Fermi wave vector would extend. The band structure becomes flatter here at the Fermi energy, so you get an increase in the effective mass associated with that particular band. and you have a large Fermi surface. So this is a change when you go from, say, high temperature, where you don't have the formation of these Kondo singlets, you don't have bound states and a coherent situation. You have regular band structure and a small Fermi surface, and then as you go to lower temperature and you get into the Kondo state, if you like, the Fermi surface will change from a small Fermi surface that doesn't include the f-electrons to a large Fermi surface that does include the f-electrons. Okay, when we have a weak coupling, so we're not in the limit where we have a strong Kondo effect and the f-electrons are actually hybridized into the conduction band, you still get an interaction of the conduction and the f-electrons, and you get a polarization of the conduction electron C, and then you basically then get, if this is a nearly localized moment, you get a disturbance or an exponential decrease in the electron density here, and then this continues as a Friedel oscillation or a kind of a sinusoidal oscillation as you go further away from the original disturbance or the original localization. So this polarization of the conduction electron C is the well-known RKKY interaction. It's antiferromagnetic exchange. It's indirect exchange between the local moments via the conduction electrons, and this tends to lead to antiferromagnetic order. And this, I've taken this introduction from Pierce's very nice book. This is the Hamiltonian for the RKKY interaction, and this is the J term here for the RKKY. This J is still the strength of the hybridization between the conduction and the f-electrons, and these are the other quantities. This is distance, so this gives you the oscillation as a function of distance as you go away. So when you're in the weak J limit, you still have a renormalization of the conduction band, but it's different. So the renormalization of the conduction band in the case of the well established Kondo effect, and the weaker J when you don't have the Kondo effect, but you have this antiferromagnetic or the indirect coupling between the local moments, it looks as the following. So this is the unmodified band structure. The F levels sit here, some distance quite close. This is typically only a few hundred millirydbergs or some small distance from the Fermi energy. Here in this case, there's a resonance here at or a distortion, a resonance here at the F level, and this gives you a distortion associated with the distortion, at least at the Fermi energy. So although the Fermi wave vector is unchanged, so the Fermi surface doesn't change size, you can still have a renormalization of the masses. So even when you're not in the Kondo state, you can still have rather heavy fermions due to this type of renormalization of the band, this flattening here of the band at the Fermi energy. So there are many ways to get a heavy fermion. When I was preparing this talk, I was much more ambitious than I ended up being, because I realized there wasn't enough time, but it's possible to have an interaction between F and conduction electrons in a number of channels. It doesn't just have to be this antiferromagnetic exchange or indirect exchange with RKKY or the Kondo effect. So F electrons and conduction electrons, crystal field levels can be involved. You can have coupling via magnetic excitons or by quadrupolar excitations. So there are very many ways to get heavy fermions. But in the majority of the heavy fermion systems, at least the cerium and the uranium systems, it's this Kondo effect competing with the RKKY effect that is dominating most of the physics, and that's what I'll concentrate on here. So this is the standard model. This is the very well-known Doniak phase diagram, so I won't spend much time describing it, but it shows what I've just been talking about. This is the magnetic order. I'm going to think primarily about antiferromagnetic order, and then the heavy Fermi liquid, where you have the Kondo effect well established in this part of the phase diagram. And this is, again, this coupling between the conduction and the F electrons. So at small j, you have the antiferromagnetism dominating or order in this region. And then here you have the heavy fermion system. This transition between the two in this standard model, or this rather kind of famous and well-known model is a continuous quantum phase transition, but we know now that there is a lot more to it, that this is kind of a starting model, and that the heavy fermion systems actually throw up a lot more than is just represented in this simple phase diagram. So in fact, this is not always a continuous second order phase transition. There are also perhaps occasionally additional energy scales or dynamical scales associated with this phase transition here. So there's actually a lot more physics associated, even just thinking about antiferromagnetism to paramagnetism, let alone other types of order in this system, in these materials. But for now, we'll think about this basic picture, and I will extend on that a little bit. So in reality, the heavy fermion systems are highly tunable. So this phase diagram, it's very easy to get, well, relatively easy to get across it. So if you start somewhere here with magnetic order, it's not that difficult to tune in the heavy fermion systems to get towards, yeah, well, at least to suppress the magnetic order and to move to some other region of the phase space. So particularly high pressure is a very strong tuning parameter. Magnetic field, of course, is what I will be talking about primarily, but chemical doping is also a way of getting, affecting this Kondo coupling and moving yourself across this phase diagram. So it's particularly influential on all of the properties of the materials, because in these correlated electron systems, of course, all of these degrees of freedom are very strongly coupled. So if you modify one, you're changing the others quite a lot. So if you, this is a phase diagram for cerium, rhodium, indium 5. I put the references down here. It's a schematic phase diagram, but it shows high pressure as a function, well, high pressure versus magnetic field phase diagram. At ambient pressure and zero field, it's an antiferromagnet, but as you increase the pressure, you suppress the antiferromagnetism, and superconductivity will appear here. If you increase the magnetic field, you also suppress the antiferromagnetism, and there's some change measured in the antiferromagnetic state before you suppress antiferromagnetism completely at very high magnetic field. So there are two quantum phase transitions here. With pressure, you can change the Coulomb interactions with magnetic field, well, amongst other things. With magnetic field, you can change the exchange, you're orienting the spins or trying to align the spins. So you're doing different things when you go in each of these directions, and indeed you get different physics. But also the things like the Fermi surface, which we can measure via the Haas-van Alphen oscillations, for example. Very different things can happen in these two different regions, and that's what I will talk about in the rest of this talk. Tuning with pressure, I said it's relatively easy to go from here to here. Of course, it's not the experiments themselves are rather difficult, but we do have the capability to do that. And of course, magnetic field is in fact a fairly easy tuning parameter. It's reversible and you can just sweep the field up and down. Doing the actual measurements in high field is more difficult, but it's possible. And this is one of the most famous experiments, I think, that we have in the heavy fermion systems. This is the effective mass measured via the Haas-van Alphen effect at high pressure, and showing that there's a divergence of the mass here associated with the change in the Fermi surface from this antiferromagnetic phase to the paramagnetic phase. So it's always nice to quote Shakespeare, and I think if he was working on heavy fermions, he would have said something like this. And this is, you know, with the heavy fermions, they're all heavy in some way. Some of them start off very heavy, but if you tune them, they can get lighter or they can get heavier. And it's certainly looking at things like the effective mass in these materials gives you a lot of information about what's going on. And what I will talk about in the rest of the talk are measurements of the de Haas-van Alphen effect, where we have extracted the de Haas-van Alphen frequencies, which give us a measure of the shape of the Fermi surface, and the effective mass, which gives us a measure of the renormalization associated with the f-electron and conduction electron coupling. And in particular, we'll look at how the Fermi surface changes as you go from something like an ordered region to a paramagnetic region. Okay, as a kind of break, this hour talk is rather long, so by way of a short break, I'll just say a few things about doing measurements in high magnetic fields. So historically, Leiden in the Netherlands was the famous place for low temperature experiments. And then De Haas and Van Alphen, of course, were also there. And De Haas was in charge of the high magnetic field laboratory. So the highest magnetic field in the world at the time was created by this electromagnet, which you see he's standing proudly in front of. And this is a 2 Tesla magnet. At the moment, we have up to 45 Tesla DC field with effectively electromagnets. But this was the state of the art at the time. And he wanted to put the magnet together with the very low temperatures that were possible in Leiden to look at things like the resistance of metals and magnetism, to try and understand what was going on. But of course, it was very difficult. So you could get the magnet, which was one thing, but then to do the measurements that you needed was another thing. And this is something that we still have now. So in the high field laboratories in Nijmegen, Grenoble, Toulouse, and Dresden, the European ones, also in the United States, in Tallahassee and Los Alamos, and in Japan, in China, Korea, and in the high field laboratories around the world, we have a lot of expertise in actually developing high magnetic fields, but the instrumentation that we have is also important, the experiments that we can do. And it's not totally straightforward to continue your zero field experiments in high magnetic field. So doing things like resistivity is relatively straightforward. The Haas-Van Alphen effect is a very nice measurement to do in high magnetic field because it becomes effectively exponentially more sensitive as you increase the magnetic field. Specific heat is still a very difficult measurement to do. It can be done in the DC fields rather well, so up to 35 or 45 Tesla. Doing heat capacity measurements in pulse field is more difficult. Susceptibility measurements are relatively straightforward, but things like neutron, I mean, I didn't talk about measurements like X-rays or neutrons that give us things like the dynamical susceptibility or the spectral function if you're thinking about optical conductivity or X-rays perhaps. And these are things that at the moment, we don't have them established in the high magnetic field laboratories, but in Toulouse, for example, they've developed a sort of a mobile high magnetic field magnet. It's a pulse magnet that they can move around, and this can be taken to places like the ILL, and then you can actually do very high pulse field experiments with the neutron scattering setup. Now it takes a lot of time. It has to be pulsed over and over and over and over and over to get resolution, but these are quite important developments, I think, that are extending our range of measurements that are possible in high magnetic fields and that are really going to be allowing us to shed a lot more light on some of the dynamical properties of materials, particularly, and I hope also of heavy fermion materials. Combining all of that with the low enough temperatures to capture the energy scales relevant for heavy fermion systems is another complication. But I think that this is something that's really a good step forward. So that's the historical and forward-looking experimental interlude. And I want to talk now about, just keep an eye on the time, that's okay, quantum criticality and how the material, in particular the Fermi surface, changes across quantum critical points in heavy fermion systems. So this again is the famous ytterbium rhodium 2 silicon 2 phase diagram, and the quantum phase transition here as a function of magnetic field. This is cerium indium 3, again, a very famous phase diagram that everybody is probably familiar with, and uranium germanium 2. So this is a ferromagnetic system. I'm going to talk about antiferromagnetism, and I'm going to talk about primarily about field tuning, although not about ytterbium rhodium 2 silicon 2. So in heavy fermion systems, you could say that there are at least 2 types of quantum phase transition. So this is zero temperature phase transition tuned either with pressure or field or with some other chemical doping, some other tuning parameter. One would be the spin density wave type. So this assumes that the f-electrons are hybridized with the conduction band in both the antiferromagnetic and the paramagnetic states. When you go through the phase transition, any change in the Fermi surface should be very minor and it should be smooth. So the ordered phase near the quantum phase transition can be just described in terms of a spin density wave of heavy quasiparticles. And then as that is suppressed, you go into a paramagnetic phase without too much change of the Fermi surface. Another possibility is a local criticality scenario, or the Kondo breakdown scenario, where when you go from the paramagnetic phase, from the well-developed Kondo state into the antiferromagnetic phase, the heavy quasiparticles just break apart. So the Kondo singlets, they don't kind of come apart slowly, that they break apart directly, and the f-electron localizes at the, goes from being itinerant, incorporated in the Fermi surface, so hybridized into the conduction band, to being localized and a small Fermi surface then in the antiferromagnetic stage. So in this stage, you just have local moments in this antiferromagnetic phase, and the Fermi surface has to change abruptly at the quantum critical point. So when you go from paramagnetic to antiferromagnetic, you have a large to small change of the Fermi surface abruptly. So this is something that you would be able to measure rather straightforwardly. Well, in principle. And then, of course, you can ask the question, do all antiferromagnetic heavy fermion quantum critical points fall into one of these two categories? Of course, the answer is no. But I will talk about these two. These are, there are important questions in a number of systems, whether which type of quantum critical point we observe and how the physics that we observe is related to the type of quantum critical point that's there. So I will just talk about these two, also in view of time. Okay, to summarize the two pictures, so there are people probably listening that are better qualified than me to talk about this. But this is the spin density wave picture. So this is a rather conventional phase transition. So on our kind of canonical Doniak phase diagram, this is the type of continuous second order, probably phase transition that you would have. So it's a conventional quantum critical point. The phases are distinguished by the development of an order parameter in the ordered phase and spontaneous symmetry breaking on this side. There are fluctuations that you can describe and predict associated with the development of the order parameter. So this is a kind of a conventional phase transition. The local criticality picture is somewhat different. In a number of systems, ytterbium rhodium-2 silicon-2 is one, but there are others. There's an unusual scaling observed in this particular region of the phase diagram. So this is not a straightforward phase transition from order to disorder, quantum order to quantum disorder. So if we have an unusual scaling, and the idea is that that the f-electron just becomes localized as you go from the heavy Fermi liquid phase into the antiferromagnetic phase. You have an abrupt localization of the f-electron right at this point, that there are new critical modes associated with this, not just the fluctuations of the order parameter, but additional modes, and that this changes the dynamics of the system and gives you influences different physics. The Fermi surface, to identify this, we should be able to measure the Fermi surface, and we should see a change in size. So you have a small Fermi surface on the ordered side and a large Fermi surface on the disordered side, or on the paramagnetic side. So the material that I want to talk to you about, I mean, I'm speaking about just these two particular scenarios because I want to bring this to bear on the materials that I'm interested in at the moment. And this is the cerium M3+2. That sounds a bit complicated, but the simplest of this family is cerium indium-3. So this is a cubic crystal structure. Cerium, that should say, cerium rhodium indium-5 or cerium cobalt indium-5. The 115 materials are the next with a layer in between member of this family. This is tetragonal, and this is extended tetragonal. It's body-centered tetragonal, but has it's a more two-dimensional version of the 115 members of the family. So cerium platinum-2 indium-7 is the material that I'm going to talk about. And all of these materials become superconducting when you suppress with pressure. But what happens with high magnetic field is a question that hasn't really been answered very clearly, at least not uniformly across this series materials. So the Néel temperatures are relatively comparable. So they're all antiferromagnetic at ambient pressure and at zero field. When you apply pressure, you get superconductivity appearing at comparable pressures in each case. And then TC is much lower for cerium indium-3, and it's comparable here for these two systems. The magnetic structures are also similar. So cerium, platinum 2, indium 7. The moments are in the plane. They're sketched here. This is from Matthias Raber. They're about 0.45 or half the Bohr magneton per cerium at 2 Kelvin. And the moments rotate by 90 degrees from one plane to the next plane. Comparing that with cerium, indium 3, the ordering is similar. It's half, half, half also in cerium, indium 3, similar Bohr magneton per cerium atom. And then the rotation in this case is 180 degrees from one plane to another. So that's from one cerium, indium 3 plane to another. And that's also what I mean here. The moments rotate from one cerium, indium 3 plane to the next cerium, indium 3 plane. In cerium, rhodium, indium 5, the ordering vector is slightly different. So this is incommensurate with the lattice. It's more like a spiral or kind of twisting moment. And this is more like 0.75 Bohr magnetons per cerium, and the moments rotate by 107 degrees from one plane to another. So these two are commensurate, and this one is not. Okay, so the phase diagrams of cerium, platinum 2, indium 7 look a little bit like this. So this is temperature as a function of pressure, and then this one here is temperature as a function of magnetic field. So with pressure, as I said, you can suppress the antiferromagnetism. Well, first it's enhanced slightly, and then you can suppress the antiferromagnetism, and then superconductivity develops around the region of 3 gigapascals. So this is from a series of different measurements, transport, susceptibility, various different measurements are all shown on this phase diagram. As a function of magnetic field, again, you suppress the antiferromagnetism. So this is these are measurements from heat capacity, which is from this article here. It is quite difficult to do heat capacity in the pulse magnetic field. So we've been trying to find a way to extend this, phase diagram, but it's very difficult actually to identify this antiferromagnetic transition. So in specific heat, we see very sharp feature for the antiferromagnetic transition here, and it becomes less distinct as we go along. There we just, we now have done measurements actually up to 35 Tesla, but this just extends our phase diagram to here. So this blue line is an extrapolation. It's a guess. It could have a completely different shape. It could be first order. It could do anything. We don't know. We've only been able to measure up to here. We've tried also measurements of ultrasound. The superconductivity, Piers had a question about the superconductivity in cerium, platinum 2, indium 7. It looks like it's D wave. It seems to be quite similar to cerium, rhodium, indium 5 in most respects. The TC is about the same. The critical field is about the same. Yeah, that's kind of as much as I can say about the superconductivity in cerium, platinum 2, indium 7. It hasn't been measured very much, so this material is not even a fraction as widely measured as cerium, rhodium, indium 5. Good single crystals only became available, I think, a few years ago, and even then not so widely measured. So apart from knowing that the superconducting dome looks kind of like this, and that there have been a few measurements, NMR, I think.
Alex, the transition temperatures seem to separate out in the antiferromagnet between rho equals 0 and I guess diamagnetism. Is that thought to be filamentary or something like that, inhomogeneous?
I think this is the kind of scattering here on the picture, and this separating is to do with inhomogeneity in the crystal structure. So it's very layered, and also the higher quality crystals show a more uniform phase boundary. So I think it's probably to do with crystal quality.
Thank you.
Yeah. Okay. So they look a little bit like this, and there are two quantum phase transitions. One here is a function of pressure, and then there is one over here somewhere, but we don't know exactly where. So let me make the comparison of the phase diagrams. Let me check the time of these materials. So this again is the pressure versus magnetic field phase diagram of cerium, rhodium, indium 5. And I've just sketched on here what we believe to be the size of the Fermi surface. And when I say the size of the Fermi surface, I mean whether the f-electron is in the Fermi surface or whether it's hybridized with the conduction electrons and itinerant. or at least partially itinerant. So this would be the large Fermi surface, which is represented by a large gray circle, or whether the f-electron is localized, and this is represented, this is the small Fermi surface, and this is represented by a small gray circle. So for cerium, rhodium, indium 5, these measurements of Shishido that I showed, where the effective mass diverges close to the change at the suppression of the antiferromagnetism. This is a transition from a small to a large Fermi surface. This is quite well established in this direction. And this is thought to be an example of Kondo breakdown. So you have a large Fermi surface that suddenly becomes small at this quantum phase transition. In this direction, at around about 30 Tesla, it's thought that there's a metamagnetic or a localization transition inside the antiferromagnetic state. So antiferromagnetic order changes a little bit to a kind of a spin density wave out here. And then this is a continuous behavior of the Fermi surface from large to still large as you go through the actual suppression of the order at this point. Cerium indium 3 is the other member of the family. This has a large, or at least the Fermi surface is small geometrically, but it does contain the f-electrons. There are small hole pockets of the Fermi surface observed in this region at a very low magnetic field. At high pressure, this also has a small dome of superconductivity, and the Fermi surface is thought to be large, or it has been measured to be large outside here. So there's probably no transition of the Fermi surface this region. Going in this direction as a function of magnetic field, the Fermi surface is small, so localized f-electrons in this region, and it's not clear. There is a feature in the, I think this is the magnetic susceptibility perhaps, or magnetization of cerium indium 3 here, and it's thought that this could be a change in the Fermi surface again within the antiferromagnetic state. But this time it's going the other way, from large to small. So it's not a consistent picture across these materials. And then this is cerium, platinum 2, indium 7. There's a question about, does the information on the Fermi surface size come exclusively from DHVA oscillations? Are there problems then due to finite extent of certain phases in applied magnetic field? Yes, at the moment, this information on the size of the Fermi surface is coming from de Haas van Alphen or Shrubnikov-de Haas oscillations. So by measuring, actually using the frequency of the quantum oscillations to measure the size of the Fermi surface. Yeah, by finite extent of certain phases, you mean just the accessibility of these phases? There are problems in being able to measure. There are problems in being, you need extremely high crystal quality to be able to be sure that you're actually measuring all of the Fermi surface and being able to resolve it. Also, you mean perhaps as a function of temperature. So you need to measure the effective mass in quantum oscillations by measuring the temperature dependence. And if you have a limited temperature range over which you're in a certain phase, then indeed you can come into trouble. So if you have to measure your temperature dependence across a phase boundary, then it's difficult. So you have to do the best that you can. Yeah, the things that they're rather heavy. So the masses, even the ones that are not most strongly renormalized, are still quite heavy. They can be 10 electron masses or 7 or 6 or something like that. So the temperature dependence is still quite strong. So you don't need to be over a very wide temperature range in a specific phase to be able to measure them. Okay, so then this is cerium, platinum 2, indium 7. So again, with pressure, we get to a superconducting phase. And it's believed that there's a Fermi surface transition in this direction, that it's large Fermi surface on this side and a small Fermi surface on this side. With magnetic field, it's not completely clear what's happening at zero field because we can't measure the de Haas van Alphen effect in zero field. So in ytterbium, rhodium 2, silicon 2, you can see a jump in the size of the Fermi surface by looking at a jump in the number of carriers in the Hall effect. But this measurement hasn't been done here or doesn't show anything in this material. So we don't know exactly what the size of the Fermi surface is at ambient pressure and at zero field, but at relatively high magnetic field, there looks like there's a large Fermi surface, at least according to measurements done here, which I'll show you in a moment. And then at higher field, it's thought that around about this field that there is a change in the Fermi surface. So this, whoops, I don't know what that is. It looks a little bit similar to cerium indium 3, where at some high field, there's a large to a small change in the Fermi surface within the antiferromagnetic phase. And then out here, we don't know, we assume it's still small. Okay, so these are the measurements I was talking about. These were done in Tallahassee. These are tunnel diode measurements of cerium, platinum, 2, indium 7. So these are transport measurements, basically. So it's a metallic system, and the tunnel diode is measuring at a relatively high frequency, but effectively it's probing the skin depth of the material, so which is proportional to the resistivity, or is related at least to the resistivity. So you can, from the change in the frequency of the tunnel diode frequency, or the tunnel diode resonance frequency, as a function of magnetic field or temperature, you can extract information about the resistivity. So this looks a little bit like resistivity as a function of field. They saw a strong feature here around about 45 Tesla, which is what gave rise to this discussion about something happening at 45 Tesla in the phase diagram. Below 45 Tesla, they see a certain set of quantum oscillations, many low frequencies, and a field-dependent quasi-particle mass. And then at high frequencies above 45 Tesla, they see some higher frequencies emerge. So this gamma and these higher frequencies start to show up in their data above 45 Tesla. So we did measurements too. This was one set of measurements, and there were still some questions about what happens at very high field and what's happening at lower field. So we were interested in looking some more at this material. We did not tunnel diode measurements, but torque measurements. So these were done in Grenoble and in Nijmegen and in Dresden. I will also show you some pulsed field measurements just before I stop. The experimental technique is that you put your sample on a cantilever. The magnetization of the sample, so M cross B is the torque, and as you change the magnetic field, the magnetization changes, your torque changes. In this case, the capacitance between the lever and the bottom plate would change, and in this case, the lever flexes, and the resistance of the legs of this lever will increase or decrease in resistance as the lever goes up and down. So this gives us, they both give us rather sensitive measures of the torque. So we see very nice de Haas van Alphen oscillations. This is a magnetic field up to 35 Tesla. This was measured in Grenoble. So I failed to write it down anywhere, but this is work actually is being led by Ilya Shakin in Grenoble. And the samples have come from Rikyo Setai in Niigata in Japan. So this is a collaboration that we're working very closely on, but Ilya especially and his students have been leading this work, and I'm involved a bit. At least we did these measurements here. Well, we've done all of the measurements together. These are the microcantilever measurements, but they give us the same results. So these are 50 millikelvin in a dilution refrigerator in Grenoble, and similar results were obtained in Nijmegen. So we see below 24 Tesla, this is just this region that I've highlighted here in blue. It's not very much of the overall one. Actually, no, this is just up to 2 Tesla. And below 24 Tesla is from here. So it's this region of the oscillations there. We see a very low frequency here, and then a few kind of at 1.5 kilotesla frequencies, so quite low. When we look at this region, which is above 24 Tesla, we see some 24 was, we just detect, it wasn't a number that we picked, but we did analysis over the whole field range kind of sequentially, and we found that there was some kind of change in the spectrum at 24 Tesla. So above 24 Tesla, we see the emergence of these high frequencies, and these are the frequencies that correspond to the high frequencies that emerge here. If you look at these kiloteslas, this is 6, 12, etc. This is not quite 12, but these 6 and 4 Tesla frequencies are the ones that emerge. But we see them not above 45 Tesla, but above 24 Tesla. So at a much lower field than they were observed in the previous work. This is a comparison of the data in Nijmegen and Grenoble. So it's the same. This is a much higher temperature, so the resolution is worse. But these frequencies, this one is actually there if you zoom in, but these frequencies are still observed, and the splitting is observed in both sets of measurements on both sets of samples. Okay, so we looked at the masses. So in the earlier work, the masses were field dependent at low field for the lower frequencies. We didn't really see any field dependence. So this is how the de Haas van Alphen mass is extracted. So this is the amplitude. If we look back, the amplitude of these oscillations. So you just take at different temperatures and plot the amplitude versus temperature. Here we have amplitude and temperature on the x-axis. And then we can fit these to the Lifshitz-Kossovich expression. I gave the damping factor at the beginning of the talk. So this is an x over sinh x function that allows us to extract the effective mass of the quasiparticles. So they're small, 2 electron masses, 6 electron masses, 5 electron masses, so not really very large. At low field, the masses associated with the lower frequencies are also in the order of 2 electron masses. So they're renormalized, but they're not very strongly renormalized. The fact that we see these frequencies and their mass, there's very little field dependence, nothing really changes going across this region at 45 Tesla. So from 24 Tesla all the way up to the highest field that we measured, which I'll show you in a moment was actually 70 Tesla because we did the measurements in pulsed field as well. We see no change in the Fermi surface, at least in the dominant branches that we're able to observe via the Haas-van Alphen effect, and not really any change in the effective masses either. So this indicates actually that the f-electron is localized all the way from 24 Tesla up to the highest magnetic field. More evidence is if we compare with the band structure calculations. So these are calculations for a localized system. So it's lanthanum, platinum, indium 7. Lanthanum has no f-electrons, so this gives you a localized picture. Cerium, platinum 2, indium 7, this is calculated with the f-electrons part of the Fermi surface. So itinerant f-electrons, this would be kind of Kondo scenario. Or any scenario in which the f-electron becomes part of the Fermi volume. They look rather similar and the picture didn't come out so well, but this is basically what you need to pay attention to, is that if you have a transition from localized to itinerant f-electrons, the gamma frequency should disappear. So that's this one here. And then the gamma frequency is this small one. But even though it's small, this one is just really big. So it's still quite well resolved and we could measure it very well. And also the frequencies of the alpha and beta oscillations should shift. Why do we only see the frequencies above 24 Tesla? Are we then shifting our Fermi surface change from 45 Tesla down to 24 Tesla, that we see nothing and then we suddenly have these frequencies appearing? That's not the case. Actually, it's related to magnetic breakdown. So in fact, we're looking at the system in an antiferromagnetic phase. This isn't calculated specifically to be antiferromagnetic. And in fact, the magnetic Brillouin zone is smaller. But when you reach a certain magnetic field, you get magnetic breakdown between the orbits, folding of the Fermi surfaces. But you can jump with magnetic breakdown through those folded parts of the Fermi surfaces, and then you see the regular orbits that you would see in a paramagnetic system. So the calculation, I don't show it, but it's a straightforward calculation of what the magnetic breakdown field would be, and this should be about 25 Tesla or above in this material. And this corresponds very well, but we see these frequencies start to appear above 24 Tesla. So we're seeing them in the antiferromagnetic state because of magnetic breakdown that occurs above 25 Tesla. So this is a comparison of the angle dependence of the de Haas-van Alphen frequency. So the oscillations that you see, there are multiple frequencies in the curve, and we can separate them using Fourier transforms, as I showed. And the angle dependence gives you basically how, if I go back to the picture, if you measure the angle dependence, your angle dependence is the orientation of the magnetic field for this orbit is pointing in the direction that's straight up and down on this page. But if we tilt this, we get the shape of the Fermi surface as you go all the way around. And so you can get a better idea of what the shape of the band structure.
Alex, we've just passed 5 o'clock, so we're going into question time.
Okay, I'll just have a couple more slides and then I'll stop. It's just there was a tiny gap in the middle, so just give me one more minute.
Absolutely.
Localized f-electrons, the calculations are in black and the data are in color. So the circles here are all experimental data of the frequency as a function of angle. And you can see that for the localized case, they agree extremely well. This is the calculation for the itinerant case. You see the gamma frequency disappears in the calculation for the itinerant case, but we have data there, so it really looks like we have a localized scenario. The alpha and beta frequencies agree extremely well with the localized case. We also measured the non-magnetic analog. So Single crystals of lanthanum, platinum 2, indium 7 are not available, at least not in good quality. I think actually they're not even available at all. But praseodymium, the f-electrons in praseodymium are well known to be localized. So we measured praseodymium, platinum 2, indium 7. We had nice single crystals of that. So this is definitely a localized system. The data look very nice. The frequencies are similar, and you can see that the blue is the praseodymium compound and the red is the cerium compound, and they're really identical. They're sitting right on top of each other. So to us, this is rather convincing evidence that the f-electrons are localized and the Fermi surface is small, all the way up to very high field in cerium, platinum 2, indium 7. We did also pulse field measurements up to 70 Tesla to confirm, to look at this 45 Tesla feature and to see what happens there. But we see also no change right up to 70 Tesla. So these are examples of the data across that field region. This is the highest field, this is 1 over B, and this is the lowest field. And these are the Fourier transforms giving us the frequencies, so the areas of the Fermi surfaces, the alpha, beta, gamma, they're unchanged from, this is a region from 30 to 35 Tesla up to 50 to 60, 70 Tesla. Alpha, this gamma frequency splits a little bit, but it's unchanged. We don't see it at very low field. And these ones don't shift and they're unchanged. So we say that the f-electrons are localized up to 70 Tesla. Then the very last thing in the last 1 minute that I will steal from the question time. These are the data, the torque data as a function of field up to the maximum field. So these are data from the, these are in the PhD thesis of Matthias Rabe. I think I have the reference maybe on the next slide. But this is a clear feature at around 45 Tesla. So this is as a function of temperature. All of the different colors are different temperatures given here. So this one is the highest temperature, but it doesn't move very much. So this corresponds to the feature in the tunnel diode measurements that was thought perhaps to be a Lifshitz transition. So a change of the Fermi surface from localized to itinerant, so from large to small. But we see that there's very little temperature dependence, and we've also seen that there's no change of the Fermi surface across this transition, but it still leaves the question as to what that is. If we plot it on the phase diagram, this is cerium, platinum 2, indium 7, temperature of that feature at around 45 Tesla. You see it's very weakly temperature dependent. And so we're supposing at the moment, or we're proposing that this is a valence crossover. This is supported by theoretical work, and this is as a function of pressure here. The antiferromagnetism is suppressed, and a valence transition is also proposed and perhaps observed in materials, ytterbium and cerium-based materials, as a function of pressure in this way. In cerium metal also there is a valence transition, so it's known that this physics is happening in this system. So we suspect that this is a valence transition at 45 Tesla, and the Fermi surface does not change across this transition. The effective mass does change a little bit. So this is the effective mass as a function of field. And you can see that there is a change from 3 to 2 or so. Piers, is the valence seen to change from core level spectroscopy? We don't know. I don't think it's been done. It would be nice to have a look in another way. So this is quite new data, reasonably recent. It's at 45 Tesla, and it's difficult to do these measurements, I guess. So we're looking at things like ultrasound as well, and various things that we can actually do at high magnetic field to try and see what's happening. But it's not clear whether there's a field-tuned valence transition from any other measurements. So it's a proposal at the moment. So the neutron scattering, are there any measurements of inelastic neutron scattering to show that the f-electrons are localized? No, I don't think so. The neutron scattering was done to determine the magnetic structure, but we didn't say anything about the f-electrons in that. It was elastic scattering. So yeah. So this is a very good question. Why extrapolate to the quantum critical point? It could be the quantum critical endpoint of the valence transition. Exactly, I agree completely. We made this before we had done these measurements. We measured the heat capacity up to 35 Tesla, And we saw that we were coming down here with the antiferromagnetic transition, and we thought, okay, maybe it's logical to extrapolate this to a quantum critical point. And then we suppose, what type of quantum critical point is this? Is there going to be a Fermi surface transition? So the extrapolation was done really thinking about the phase diagrams of the cerium, rhodium, indium 5 and cerium, indium 3 and the other other members of the family. So there's not much physical basis for this extrapolation. It could indeed come down here, or it could come down much more sharply. As I said, it's somehow slightly mysteriously difficult to measure this antiferromagnetic transition. We don't see it in magnetization. We can't see it in the ultrasound. We can't, it doesn't show up very clearly. It doesn't have a clear signature. So we would like to try to expand the heat capacity. It's not possible to do magnetic susceptibility because the samples are very tiny platelets, and we can't get enough of a signal from a susceptibility measurement to try and get a thermodynamic signature of this phase transition. So this extrapolated QCP is indeed, it's just, you know, imaginary. It's not something that is has any basis, and it could be anywhere. And one of the things that we're thinking about is whether it could be related to the endpoint of the valence transition. Although you would expect the endpoint of the valence transition to be maybe at negative temperature in this system. Somebody asking a question?
Yeah, I asked that question. Thank you for your answer.
Okay, yeah. We do see a change in the mass, which could also be associated with the change in the valence will be tiny, right? It will be some tiny fraction of the valence change. It's not a localization, you know, it's not an f-electron suddenly jumping into the Fermi surface. But this is interesting. And as I said, it's not something, they're relatively new data, and we're still trying to think about what they might mean. All right, I took more than 5 minutes of the questions. Just to summarize, I show this picture again, and it's changed now. So the original picture I showed you was large and small here at this 45 Tesla transition, but I think we've shown at least from 25 Tesla that we have a small Fermi surface with localized f-electrons that continues to be like that all of the way up to 70 Tesla. So we don't know that the critical field is around 55 Tesla. This was an extrapolated point that we imagined it should be about there based on the type of behavior that we see in other members of this family. But we do see now this transition that we think is related, well, not transition, but probably crossover related to valence, a change in valence in the material about here. And something has to happen in this material because we have a large Fermi surface up here and a small Fermi surface over here. So we know that there has to be some kind of transition in the material somewhere in this region of the phase diagram. And I think I should stop there. And thank you for your attention. Okay, there are plenty of questions.
Great. I think before getting on to the questions, we should all thank Alix for a fantastic talk in the usual way. Unmute yourself. Okay, so to questions, Alix, you can see some in the chat there. You may take them as you.
Yeah. Okay. From Alix, would it be possible to look for a valence transition with excess measurements?
Sorry, please mute unless you're actually asking a question. We have some.
So I can't hear anything at the moment. Is there an audio question, or should I continue with the
I think that was just somebody who accidentally didn't remute after the clapping.
Then I continue to try and answer Alix's question. Using the Toulouse, look for a valence transition using the Toulouse portable pulse magnet. It would be a nice thing to try, wouldn't it? The thing with them, I think it's a fantastic thing. I think they've really done something special with this portable magnet, and people should really look into using it whenever they can, which is not to say that everybody should use it for trivial measurements, but I think it would be a nice thing to try, but a valence transition, it will be a very small change in valence, and it's showing up as a small kink in the magnetization, if that's what it is. But in terms of how we would be able to do it with excess, I just don't know. I'm not an expert enough in these types of measurements. But the idea with the Toulouse magnet is that you can bring it along and attach it to the X-ray or to the neutron scattering equipment. So in principle, you should be able to do it. But there might be people listening to this talk that know much better than I do whether that's feasible or not, or whether there would even be a signal that we could measure.
Hi, Alex. There's a question from Sentil. He's raised his hand.
Yep.
To ask a question. Sentil, if you'd like to.
Yeah, so thank you for that very nice talk. So maybe you said this, but I just want to make sure the high field non-magnetically ordered Fermi surface state.
Mm-hmm.
Do you know if the spins or the F moments are just spin polarized by the high field in that metal?
Yeah, we don't know. Of course, you would imagine that you would have, at least if you had a Kondo effect somewhere, that would be quenched by 70 Tesla or so, and that you would be polarizing the spins. So we don't know for sure because we don't have a way to actually measure that at high field, but we have to assume that it's the case, that there's some significant polarization of the material at high field. But we don't know. We don't have an experiment that we can say, yes, this really shows that we're just aligning the spins. I mean, the magnetization, it starts to saturate, but it's not saturated. That would be the best indication, I guess. So when we measure the torque, let me, if I can go back, these are the torque data. And you can see that at 60 Tesla, there's still, I mean, there's no obvious saturation of the torque data. So there's still a kind of evolution of the signal. So they're not fully polarized, at least, if that answers your question.
It's conceivable that it's only the F moments that are fully polarized, but
yeah,
not conduction moments.
But this we can't tell.
Okay.
We can only measure like from the thing that we have.
Great, thank you.
We have another hand.
You might imagine that doing neutron scattering in the portable pulsed field measurement would be able to help you with that a little bit, because you could maybe see if the moments were ordered or what the moment was at high field, and that might be able to tell you, and you might be able to see if there was a change. But again, it's a very challenging measurement. Another question?
There's a hand raised from Chimia.
Yeah.
Hi, Alex. It's a nice talk. So I have a similar question to what was just asked,
mm-hmm.
but maybe even in a larger parameter space. I imagine at higher pressure, the paramagnetic phase, there's a very limited amount of information about that as well, right? So pretty high pressure. So I guess my question is there some cousins of this material? Like, let's say instead of platinum, it would be, I don't know, palladium, nickel, in which the paramagnetic phase is more easily accessible. And if there is there some understanding of the behavior of the heavy fermion state, paramagnetic phase?
Yeah, I guess the answer is no at the moment. The cousins of this material are the 115s that we know about at the moment, and they're just as inaccessible in a way. One thing that you can do, so with cerium iridium indium 5, for example, if it's superconducting at ambient pressure, but if you dope with cadmium, you push it into the antiferromagnetic state. So with a small level of cadmium doping in cerium iridium indium 5, you get to a stage where you have a very weak antiferromagnetism that you can access or you can suppress with a very small pressure with a very small field. So it would put you in this corner of this phase diagram. So that's one avenue that we're looking at. So the cadmium doped cerium iridium and indium 5 samples are quite high quality. So we're able to observe quantum oscillations up to a few % doping at least. So that's a direction we're trying to look at, but as yet, yeah, we don't know. So no,
if I may, just to quickly follow up. I mean, 115 certainly all the different parts of the phase diagram have been looked at to various degrees. But I was just wondering whether it's 127, whether there's a palladium version or some nickel version of the.
I think there can be a palladium version, but I don't know of measurements on it. So it hasn't been widely measured yet. So this more two-dimensional version of the family is not very well explored yet. So it's maybe to be done.
Would be very interesting. Thank you.
Yeah.
Alex, there are a couple more in the chat, and then I have one person who wants to ask in person, I think, after you've dealt with those.
Okay, let me go back up. So the question I didn't answer was, how does effective mass affect the Fermi surface volume. So the effective mass doesn't affect the Fermi surface volume at all. So the de Haas van Alphen effect can measure a number of things. From the frequency of the de Haas van Alphen oscillations, you can get a measure of the Fermi surface area. So the cross-sectional area of the cyclotron orbits on the Fermi surface is proportional to the frequency of the oscillations. And if you change the angle, you can see how that cross-sectional area, if you change the angle of the magnetic field, then the cyclotron orbits are always perpendicular to the magnetic field. So you can map out what the shape of the Fermi surface is. And effectively, you can measure the size of the Fermi surface in that respect. The total volume of the Fermi surface shouldn't change, right? The number of carriers shouldn't really change unless you're taking an f-electron in or out, and then the Fermi surface can get larger or smaller. The effective mass is given by the temperature dependence of the quantum oscillations. So you can find that in a large Fermi surface, you expect that the f-electron is involved in the Fermi surface, is somehow hybridized into the conduction band. So then you would expect this enhancement in the density of states, enhancement of the mass and on all of the quantities that I talked about earlier to be there. So it's not that the effective mass affects the volume, but when the f-electron is absorbed or somehow pulled into the Fermi surface, you expect the mass to increase. So that's the relationship between the mass and the Fermi surface volume in this context. Does that answer your question, maybe? If it doesn't, you can write again and I'll try to make a better attempt. For now, I'll carry on and go to the next question. Does any other cerium, platinum, indium, etc. system show pressure-induced superconductivity? Not that I'm aware of, but I might have less knowledge than some people. So I'm not involved in growing these materials. And maybe there are people busy with growing them that have found superconductivity in other materials, but I'm not aware of anything else. Okay, so this is an answer, I think, to one of the previous questions from Christopher O'Neill. Hi, Chris. You can do high resolution X-rays here to look at the change in valence, but the change might be very small. That's what I would be afraid of, that you could really make a huge experimental effort to do these experiments, but you might not get anything in return.
Okay, so there was a question directed to me privately in the chat from Rivaz.
Yeah.
Rivaz, if you'd like to unmute yourself, you can ask the question.
Yes.
Hi, by the way.
Greetings. Thank you. Thanks, Andrew. Thank you for the inspiring talk. I have a question that's not related to the quantum critical behavior in these materials, but rather to the behavior deep in the nail state. Mm-hmm. Did you by any chance study spin zeros when looking at the de Haas van Alphen oscillations, like be it angle dependence or field sweeps at a fixed orientation?
No, we didn't. Let me go back to the, whoops, can I go back up to the, so we didn't actually see any spin zeros and we didn't go looking for them. I guess if there are a lot of frequencies and there's a lot of beating, but I suppose if we'd actually by chance seen some spin zeros, we might have looked at them a little bit more, but we didn't spend time actually looking for them or trying to understand what was happening there. Maybe we should, but no, we didn't. In that case.
Okay, thank you.
I have a question concerning your last slide. Could you go back to that, please?
Yeah, hang on. This one?
Yeah, right. Okay, so if you go horizontally with increasing field, you don't see much change of the Fermi surface, Fermi volume rather. But if you go at constant field with increasing pressure, you seem to indicate that you go from a small Fermi volume to a large Fermi volume. Much like then there could be some sort of T-star line or something like that. What's the evidence for this crossover from a large to from a small to a large Fermi volume?
So there isn't actually any evidence of a crossover here, only that it must be there because we know at zero, well, at low field at least, in this region that there's an itinerant Fermi surface, or this has been reported. And in this direction, we see that it's still a localized Fermi surface, so it's small here and it's large here. So there must be a crossover here, but we don't have evidence of it. So this is, in a way, the dream experiment, right? To go to 50 Tesla and go up in pressure. It's very difficult to do the high pressure measurements at field, but of course, people can do them. Particularly, there's been, in recent years, development of plastic pressure cells that allow you to get up to very high temperature. And there have been measurements of cerium, rhodium, indium-5, more in this region of its phase diagram recently, and things such as nematicity and other features of behavior that weren't expected are seen up there. But in terms of this material, the data that we have are all at ambient pressure at high field, and the highest data under pressure is up to, I think, about 18 Tesla or so.
Thank you.
Okay, Alex, there's a question from Catherine Goetze.
Yep.
Catherine, if you'd like to unmute.
Yes, hello.
Hey.
Hi, Alex. I have actually two questions. So when you initially said that the Fermi surface at zero field and zero pressure of the cerium platinum to indium-7 is unclear, I was thinking about ARPAs because this is what you can do at zero field. And I had a quick look. But I think there's one ARPAs paper. Do you think ARPAs could be used to kind of support your conclusions about the localized f-electrons?
I guess so. As I said, there hasn't been that much done, so I don't really, I'm afraid if there's ARPAs, I don't really know whether...
Yeah, I think there's one paper, I had a quick look at the abstract, but I'm not sure of the...
So in principle, it should be able to tell us, right? If we, as long as we're at zero field, it should be able to tell us what the, I mean, these things are very good quality surface. They're platelets, they cleave very easily. So I think an ARPAs measurement would be reliable. But I don't think there's anything suggesting that there's a large Fermi surface. So if there is ARPAs, maybe I kind of subconsciously absorbed it because I don't think that there's any evidence that there's an itinerant Fermi surface down here. And it's kind of understood that there's a transition here at the superconducting, or rather at the critical pressure, that's comparable to, I mean, one question about this transition. So NMR, or maybe it was, yeah, that's NMR, I think, as well as transport. And there seems to be some disagreement about whether the Fermi surface transition happens exactly at the critical pressure for suppression of antiferromagnetism. So it's not clear. I think the Fermi surface transition is thought to happen at slightly lower pressure than this critical pressure, so maybe even slightly within the antiferromagnetic state. So that's the only question that I'm aware of that's not really resolved in terms of large to small Fermi surface at zero or at low field at least, is a question of whether it really coincides with the critical pressure for suppressing the antiferromagnetism. But in principle, an ARPAs measurement should tell us perfectly well what the Fermi surface looks like here at low field, at zero field.
Okay, a quick second question. I was wondering about the valence transition, whether magnetostriction measurements would be helpful to clarify this.
Yeah, we're trying to do them, I think.
All right, thank you.
Okay, so there are a couple of questions in the chat, and after those, we have Chimiao with another question.
Okay, so then the next one, oops. Sorry, my chat screen is rather small, so I have to, okay. Is there some modification occurring in the Fermi surface during high field that contributes to the oscillations? So in principle, any modification of the Fermi surface will show up in the quantum oscillations because, well, if it's a modification that changes the area, you will see it. If it's a modification that changes the density of states, or somehow if the renormalization is changed, you should see it in the temperature dependence of the Fermi surface or in the field damping or something. So there are a number of aspects of the de Haas-van-Alphen effect that tell you about the quasiparticles on the Fermi surface and the shape of the Fermi surface. So we should be able to see it, but all we see is that we have features, a rather flat but clear feature around 45 Tesla in the torque, which is the one that I showed you. But the Fermi surface, the quantum oscillations don't change much. So there's this behavior here at around 45 Tesla, but the frequencies, although the background of this torque curve is changing, the oscillatory part that's on top of that doesn't change very much at all. So we don't see anything really changing across there, except the mass. So here I show that the mass does change a little bit. This is done over a kind of an overlapping field region between about 35 and 60 Tesla. And we do see a slight change in this alpha mass, but that's as much as we can say about changes in the Fermi surface at high field. If there was a change, in a big change in the Fermi surface, we would see it because the resolution is rather good for these oscillations, I think. Okay, if I'm not answering these questions satisfactorily, please write again or say so. I'm happy to expand more or to try to make a better answer if I'm not answering you. Piers, what is known about the entropy of condensation in the superconducting state, and what does the spin susceptibility look like under pressure? Is it Curie-like or Pauli-like? This might give an idea about how much the local moments are condensing into the superconducting state. I don't know. The spin susceptibility.
To give some context, Alex, for example, in the Neptunium 115 material, you see Curie behavior all the way down to TC, and also in the cerium cobalt indium 5, you see Curie behavior right down to TC. So it's curious to know what might be happening here. And also, how big is in terms of log 2, is the amount of entropy underneath the specific heat curve in the superconducting state? These are very large numbers in 115s, and so
yeah, it's also large. Oh, hang on. I don't have a copy. If Katrin is there still, she can probably answer that. It's large. I don't remember the number but it's comparable to the 115. So the gamma is comparable to the 115s, and also the condensation into the superconducting state. It's the heavy quasiparticles that are going in. So it's the superconductivity under pressure is very comparable to cerium rhodium indium 5. So the numbers are quite similar. I think the heat capacity it's a bit lower. Gamma is a little bit lower, but it's not. It's of the same type of number. I don't have the exact. Maybe can I?
And has the spin susceptibility been measured at under pressure?
No. So NMR was done, and transport has been done. We've tried to do tunnel diode measurements, which would give you some kind of hybrid of resistivity and susceptibility, but the quantum oscillations disappear under pressure when we try to do the tunnel diode measurements. So that hasn't been successful, at least not yet. Oh, okay, Katrin has just told me that the gamma coefficient is 180. So it's a bit lower than the others, but it's still pretty big.
Okay, Piers, if you're done, maybe Chimio, you can.
Thank you, Andrew. Yeah, so just to follow up on what Hubert Volonisen asked about the pressure-induced quantum phase transition at zero field. The fact that TC is quite high looks to me, sounds like very interesting transition. So I was just wondering, you mentioned that transport has been studied in that regime. Is there some characterization of the non-Fermi liquid aspects, whether the resistivity versus temperature near the critical pressure is indeed strange, etc.?
So what was measured is more tunnel diode measurements rather than, so it's proportional to the resistivity, but you're not really getting a coefficient out of it or something like that. So you can get, a general idea, but not something precise. Yeah. So
is it fair to say that there's not much known about the non-Fermi liquid aspect?
Yeah, I think there's still a lot of work. It's a very interesting material, and there's still a lot of things that need to be done. I think there are a few groups working on it, but more people could look at it maybe, and then we could get some faster progress. I think the measurements under pressure. So one thing that's interesting, I think, would be to pin down whether the Fermi surface change really coincides with the suppression of the antiferromagnetism or not. So really to measure the quantum oscillations across the transition with pressure in more detail, with better resolution, and up to possibly higher field than have been done. That would be a kind of dream measurement. It would answer a lot of questions. And then, yeah, if you could do higher field measurements under higher pressures, that also, it's that big empty region of the phase space that we'd like to try to access. But there's not that much been done up to now.
Very exciting. Thank you.
Yeah.
Okay, there's a question from Pavel Volkov. Pavel, would you like to?
Yes, so my question is about the antiferromagnetic state. It seems to extend at least up to 35 Tesla. Now, if you take the value of magnetic moment characteristic for cerium in this compound, and you calculate the corresponding energy scale, so presumably 35 Tesla would correspond to something like tens of Kelvin, at least, right? While the nail temperature is what it is, between 5 and 6 Kelvin. So isn't there a discrepancy here? Because, you know, at such, essentially the field is almost an order of magnitude higher than the nail temperature. So wouldn't you expect that this field just to completely polarize and destroy antiferromagnetism? Why does it survive to such high fields?
Yeah, it's an excellent question, but I don't know the answer to it. I think perhaps it's not surviving as well as we pretend with this line. As I said, it becomes increasingly difficult to resolve an antiferromagnetic transition as we go. I haven't done the calculations, or I don't know of calculations to sort of make a prediction about how this, as I said, was just an extrapolation that we made. So I can't really answer your question, although I will say again that it's not easy to measure. We've tried a number of different techniques that should normally give us the transition point. So even transport and the torque measurements, we would normally expect to be able to see the antiferromagnetic transition rather clearly. But in this material, and in this whole family, actually, also in cerium, rhodium, indium 5, and cerium, iridium, indium 5, cerium, indium 3, it's difficult to pick up the antiferromagnetic transition in a range of measurements. So heat capacity sees it, but others not so easily. So it might be that there is something a little unconventional about the antiferromagnetic transition in this region as well. But
is there
really
anisotropy in the applied field, or you measured only along C? Because it could be, I don't know, that some crystal field or something makes it very resilient against fields along C. Have you tried measuring
there is some anisotropy. So the system is quite two-dimensional, and so the anisotropy is actually, it's larger than for the other materials. So it's but it's not so, yeah, okay. The experimental difficulty is that these samples are little platelets. They're extremely thin along one direction, and we don't actually see very much signal when we try to measure in the field in the plane. So our strongest signals, particularly for the quantum oscillations, which is what we've been focusing on up to now, have been with field perpendicular to C. So I can't really say too much more about what it looks like with B parallel to the plane. So we just haven't done the measurements along there.
Thank you.
Kim Yao has a question in the chat. That's zero field at ambient pressure. Yes, that's right. His question was, is the gamma coefficient this value at zero field and ambient pressure? And yes, that's where it is.
Okay, I'm not seeing further questions in either the chat or with people with hands raised. So I think we should thank Alix again for a wonderful talk and for dealing with all of these many questions that we've had. Thanks.
Can't really answer all.
Thanks, Alix.
Yeah.